Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
The stuff we're doing for this year's DARPA EARS speech recognition project. Some of the meeting recording work we're doing, and then some stuff we're doing on long duration personal audio recordings. So trying to draw a chart to show how what the space of what we try to cover in the lab is. And I sort of see these three main themes: the sort of signal processing, which is the core discipline, and then machine learning is the kind of the techniques we're trying to bring in, and information extraction is kind of a fairly vague name for the kinds of tasks that we're interested in. And then different kinds of areas: speech, music, environment, different kinds of audio that we're interested in dealing with. And then maybe these four projects fit sort of around that space fairly nicely. So the first thing, eigenrhythms. This was a student project for my class, but I think it's kind of fun, and I think it has some, I'm interested in pushing it a little further. The basic idea is that when you listen to pop music, there's always this pop music has a lot of fairly strong genre characteristics, and in particular, one of the sort of defining characteristics of a lot of pop music is the drum track. And there's a very simple structure to most of that, which is sort of the bass drum, snare drum, and hi-hat. So I think this is going to play an example. Maybe not. Well, I guess not, sorry. Jeremy, is the sound up from my thing? Yeah. Okay. So let's try that again. Okay, it's a little quiet, but you know what a drum track sounds like. But the point is that with just these three instruments, but with the different time patterns you can get quite a wide variety of different sort of styles and feels. But at the same time, if you think about all the possible representation, all the possible sounds you could get by making these three different voices at different times and looping it, that's a much broader space than the entire space of all all the drum tracks you'll ever encounter in real music. So the idea was there's a subspace there. There's the actual space of real drum tracks that you come across, and can we capture that condensed representation? So the idea is we were going to try and use eigenanalysis or principal component analysis or any other kind of subspace projection to try and capture this. And the sort of what I like about this project is that it's one way of using a large amount of training data that we have available to try and do something, to try and get something out of it. So in particular, for this project, we were looking at MIDI music, which is just because the breakdown into this particular representation is already done for us. Although, in fact, getting this kind of stuff out of audio has been studied by a bunch of different people and seems to be relatively straightforward compared to other kinds of transcription. But then just taking, that you can get tens of thousands of pop music MIDI representations just by crawling the web. And so, this is something interesting maybe that we could do with that. The applications aren't really the motivation here, but the motivation is just to see what happens when you do it. But the kind of things we can do with it, well, you could imagine trying to do some kind of categorization so that you get these different kinds of underlying common beat patterns, and that gives you some kind of categories of music. And then also you can use it for synthesis to generate new patterns that are consistent with what you've learned. So the problems with doing this are that we have to make sure that when all the data, all the different drum patterns we've got are sort of conformal or lined up properly. And there are two aspects to that. One is we have to normalize the tempo. So if we just get some random piece of audio and we pull out the drum track, we have to try and make sure that we've got the sense of how long the bar is. We've got the right bar length. And then there's also the problem of getting them to actually line up properly to getting the downbeats the same, because that's also, if you shift it by half a cycle, then it's no longer lining up properly, even though it should. Okay. So this is basically this is the essence of what we did. To find the tempo, we did autocorrelation, which is a common technique. And so we just, for this two-dimensional surface, we just calculate the inner product with itself against all possible shifts, and we get a picture like this.
Do you know the labeling of which instrument is which?
Yes. So what we actually did, so we start off with this MIDI data which has these drum tracks in it, and they're actually, the way it works in MIDI is there's a set of predefined instruments, and one of the sets of voices is the drum set, and there are I guess there are 64 or 128 different drum voices, and we just count with a fixed mapping of those 64 voices to our 3 basic voices, which wasn't perfect, but was a good first step. So then we get this pattern from that. And then we do the autocorrelation. Now you see that you get all these different peaks, and this is typical that you'll get, here's the actual true period that you'd hear if you listen to it, but you also get these subharmonics, because if it matches at one of these, then it's going to match at 2 of these, etc. But there's normally ambiguity, that sometimes it may not be, the highest peak in the autocorrelation isn't necessarily the one you want to go for. So rather than trying to decide at this point what the real tempo is, we keep a number of hypotheses and carry them forward. The next part is to try and find the downbeat. So even if we know that the pattern is this long, or however long it is in the original, we don't know exactly where we should start that pattern, because it probably cycles several times over, so you've got an arbitrary starting point. And that's kind of a difficult problem to say, well, what is the property of a downbeat that we really want to get that's going to allow us to identify this? So rather than trying to come up with some music theory type definition, instead we just say, well, here's an example of a drum pattern in which I'm telling you where the downbeat is. And so just find me the alignment of the pattern you've got that best matches this. Okay. And to start off with, we could say just take if we think we're dealing with pop music and we have an idea what pop music sounds like, we could put in a very basic pop music pattern. Although what we do is then do this whole alignment process, then average all the things we get to give us this reference pattern, and then redo the alignments based on that. And that actually converged after 2 or 3 iterations. So then what we do is we take the cross-correlation between this and our original pattern scaled, so this is normalized for the tempo. And we get this cross-correlation pattern like this, and now whenever we get a high peak here, we're saying that these are points where it was a good match to the original reference pattern. And basically we just take out the highest one of these and keep that as our extracted pattern. But the nice thing we can do now is we can try this against all of the, normalizing by each of the top peaks here, and then we can take the one that overall has the best match to this reference pattern as the one we keep. So any ambiguity in the tempo here is resolved by finding the one that has the closest match to the archetypal grand average beat pattern. Okay. So then for each one of these input patterns, we end up with an extracted little chunk, and we can generate as many of these as we like. For this particular project, we just did 100 of them because we were interested in trying to do it with do genre classification, and we only had time. We had to label these things, so we labeled 100, and that was what we did. And so then we have this big stack of all these nicely aligned patterns, and we can do the PCA analysis. And this is kind of like the top. This is the typical result. So this is the average, and then these are kind of like the bipolar principal components. The top one is just adding sort of more emphasis on the main 8th note hi-hat beats, and a little bit more of bass drum in time with the snare. The second one is de-emphasizing every other hi-hat and emphasizing the snare and the bass on the beat, or the other way around if it's with a negative coefficient. And then this one's introducing some more 6/8 feel into the hi-hats, etc. It turned out that this wasn't an outstanding successful reduction, in that I think I needed like 20 principal components to account for 90% of the variance, something like that. It wasn't like really condensing down. But this was kind of like the payoff, that to sort of see these things where you can begin to see some interesting kind of correlations coming out in this representation. So the classification experiment, well, here I'm projecting of these 100 patterns, I'm plotting the first two eigen coefficients, and they're kind of spread out, but we see a couple of clusters coming out. This isn't the greatest graph. The first two letters are the actual ground truth genre, so it's actually doing very poorly for genre classification. We got 21% correct on a 10-way task, which is of 100 items, so it's that was like, I think leave one out, but it was sort of barely significant. But there's something, these clusters do represent sort of different fields of rhythm, so it is actually doing something in terms of finding different, it's doing a useful, potentially useful separation of different rhythm styles. And then the converse thing is to go from points in the lower dimensional eigenspace to generating actual rhythms. And what we can do here is just take the principal components for these, like, each one of these is 2 dimensions, so we can take the first 8 dimensions, add them up and generate a pattern, and then we can just use these as, we can sort of threshold this and use it as an input to a rhythm just to generate samples. And so I think I can play this. Yeah. So this is this. If I just click somewhere here, it just generates that, and then so the point being that every point in the space is constrained to be made up of the actual eigenfunctions, so they generate different rhythms, but those are fairly...
Should these eigenrhythms really be additive?
Well, because they come from principal component analysis.
Yeah, I mean, that's what you're assuming.
But the obvious thing to do is to look at different kinds of decompositions. So now that we've got the aligned data, we can do things like ICA and non-negative factorization, and these seem like, certainly there was some argument for why I wanted to do it, for why you might want to have a bipolar thing. What I was hoping to get was some kind of actual, there's this idea of feel in drumming. There are slight timing variations which are very important in conveying different styles. And of course, none of this came out because the MIDI data I was using was all really well quantized. It was all kind of, electronica and very. There was no real timing variation. They probably all came from beatboxes. But hopefully, if I can do this with extracted real data, then we have a little bit more of that. And then the actual surface I'm modeling here is not a binary thing. It's a little pseudo envelope. And so there's a little bit of a slope here. And so if there was some variance in where this beat came down, there would be a kind of like a little Gaussian shape, and then you could represent a timing shift by this kind of difference of Gaussian thing you could add and subtract to get variation.
And when you get to the components, do you get sort of like derivative components?
No, we didn't see anything like that, but we didn't have the small variations in timing in the data we were using.
So you're saying that once you had that more continuous, those continuous shapes, you'd actually then kind of sample from that, as opposed to actually playing a blur of drum beats.
Yeah. So what you're hearing now is just taking that envelope, but it really should be interpreted as a distribution. Yeah. But yeah, no, it's so easy to do the next step, but I haven't done it yet. I'm just running different decompositions. Okay. So I'm personally very enthusiastic about music stuff, but I don't really have any funding for it at the moment, which is why these projects sort of go a little bit and don't go much further. But I'm hoping to persuade someone to fund me for it at some point. The second project is funded by like I said, the DARPA is speech recognition work, and it's sort of more fundamental signal processing stuff that I was doing with my student Athenaeus. And it's basically a nice little twist on some old signal processing math. And we're still sort of looking for an application for it, but we're investigating uses for in speech recognition. So the twist is that that linear prediction is a very common and powerful approach in signal processing, where you model a signal as a linear combination of the previous samples plus some error term, and you find the optimal set of coefficients to minimize this error, the energy of this error. And you do this on the time domain signal, and then there's a nice interpretation of these coefficients in the frequency domain as a sort of resonant filter, because this is just an autoregressive filter, which then tells you about the spectral structure of the signal. Well, if instead the first thing you do with your signal is convert it into the frequency domain by some kind of Fourier transform, or in this case a discrete cosine transform, the discrete cosine transform gives you a real signal, gives you a pure real spectrum, but the coefficients have a spectral identity. You can do the same kind of math to try and fit this spectral sequence with some kind of autoregression. And then you end up with a different set of coefficients and a different kind of model. And what it actually does, well, here's one cute thing that came out, which points to what's happening. If this is an original piece of signal, and this is just the spectrogram of it, so we just did a short time Fourier transform, plotted the magnitude. If we just take the DCT of that, we end up with a real sequence which is the same length. And if we then treat that as a sound and plot the spectrogram of that, this is what we get. So this is, although I've labeled time and frequency confusingly, this is just the spectrogram of a piece of sound. And you could listen to it, and it sort of has these sort of like ripply things going on.
What's the difference between DCT spectrum and FFT spectrum? Are they still the same one?
They're close. So we're using DCT because originally we were using DCT because we only had the linear prediction math working for real signals. But it turns out that the DCT spectrogram is upper bounded, or the magnitude of DCT is upper bounded by magnitude of the DFT. And there's just sort of the scaling term that comes in that sort of marks it up. But what we see here is actually that, in fact, the amount to which it marks it up is quite small. So what you're supposed to see here is that this is just the 45 degree, this is a flip of this one, which is, it wasn't obvious to me, but this really does work. You can go back and try it. And so the point about, if this is true, then what we typically do in LP modeling is we take little short time slices and model the shape, the spectral shape, by fitting an LP polynomial. If we do the same thing on the DCT signal, we take a short window of that and fit an LP polynomial, then it's going to model this shape, which is now the temporal envelope of the original signal, right, because it's been flipped up here. And so we can take little short frequency chunks of the DCT, fit LP polynomials together, and we can get smooth LP smooth estimates of the energy envelope of the signal at different frequency bands.
You're using the same coefficients for all bands, so it's like one set of...
We could do. If we did that, we'd just be getting an overall estimate of the average envelope, or we can do it on separate support, and then we get different subbands. Let me see if that picture is what we have here. Okay, so this is just explaining what's happening in terms of duality. So the green line is the conventional linear prediction. We start off with a signal in the time domain. We take the linear predictor, and then if we interpret that coefficient as a polynomial in the z plane, we get this nice estimate of the spectrum of the signal, which is a smooth representation, a mean squared error, optimally smooth representation of the true power spectrum, the magnitude of the DFT. So by doing it in the converse domain, we start off with the DCT, which is now a frequency domain signal. Then when we do the LP fit, we get a smooth curve here, which is now on the time axis, interpreted on the time axis. And that's actually a mean squared error fit to the Hilbert envelope, the squared Hilbert envelope, which is the dual of the squared power spectrum. So all we're doing is we're using the same LP math, but we're using it to approximate the temporal envelope rather than the spectral envelope. And so how come, one of the things, so we're trying to use this for speech recognition. And so we're doing what Sumit mentioned. We're doing this on individual frequency subbands. This slide is trying to emphasize what we're doing different and why this can be useful. So if you like, this is actually the typical representation you might use as your first stage of your speech recognizer, which is we have individual time windows which are maybe 10 milliseconds long, or 25 milliseconds every 10 milliseconds, something like that. And then we have a set of discrete frequency bands, maybe your Mel bands or Bach bands. So you have sort of 15 frequency bands. So you have this kind of coarse, sampled representation of the spectral magnitude. And you take the DCT of that and use it as your features. It's been popular for a while to use LP smoothing of the spectrum as a pre-processing for speech recognition. And although you don't represent it as a continuous curve, what you're essentially doing is taking each one of these slices, fitting the LP to it, so you get a smooth spectrum at every time. And the smoothing is the helpful thing, because the smoothing removes some of the variation which is maybe not important to the classification task. So with subband FDLP, we take the whole of this, 250 milliseconds of speech, take its DCT, and then fit LP polynomials to different little frequency regions of the DCT, and now we'd end up with, for each of these original 15 frequency bands, we have a polynomial representation of the envelope, which is now nice and smooth and sort of low dimensional, and we can now capture the information there. And what we see here is that the polynomial doesn't involve any time quantization, doesn't involve any time windows at all. It's actually fitting down to the actual sample of the original signal. So that when there is fine time structure like this burst release here, which really gets completely blurred out by the original 10 or 25 millisecond windows, this representation really is capturing exactly where that occurs. Now, and that is information that we know wasn't available to the recognizer working on either of these representations. So,
but if your unless window is shorter in your standard picture, FFT, you probably can have similar kind of sharpness.
Right. So you could get this back by using a short window here. But the nice thing about if you did that, right, if you went down to like 1 or 2 millisecond windows here, you'd also end up starting to pick up your pitch pulses, right? Which typically is not a good thing. One of the things that one of the reasons people like LP modeling is that it does this interesting trick of allocating modeling resources non-uniformly. So you've got a whole spectrum. There are some peaks and some broad patches, and it'll put a few poles on the peaks, a few poles on the broad patches. That's what's happened here. We've got when there's sort of isolated time structure, it puts a sharp peak in here. Here's the pitch information, but it doesn't have enough poles to represent every pulse of the pitch separately, so it just sort of blurs them out. Yeah.
I'm not sure I agree with your statement that the information about the release is not available in the field. Because, the pictures look different, but it doesn't mean that the information isn't there.
Okay.
And
right.
If all you're going to do is fit Gaussians to it anyway, it's not clear that one of these is a better representation of that information than the other.
I agree.
If you had a modeling framework that could actually take advantage of that, and that becomes a very different story. Given that what most people still have are, draw measurements with mixed with Gaussians, then it's not true.
Okay, yeah, I mean, I'm basically, yeah.
Well, but doesn't it make a difference? You could conceivably be fitting the LP parameters at a finer time scale than your final representation, so it could actually be more accurate than what you just have in those blocks, right? Like you could be taking a finer time slicing over which you estimate the parameters, and then you could keep around a less.
Well, the idea here is that we actually, one possibility is we actually do the modeling on. It depends what you do with the envelopes afterwards. But you can, because you've got a parametric representation for these envelopes, like you could sample them up and then you'd be back to the original problem to do it on the original frequency domain. But you can also just try and directly go from the parametric representation of time envelopes to some features you're going to use in speech recognition, which then provide different information. But typically what we do is do this recursion that goes straight from LP coefficients to Kepstrel coefficients, which you can do out to an arbitrary order, but it still ends up smoothing them. So you end up getting something which is moving back towards here in order to be practical. We've also tried some other features where we try and do something more directly that's going to be able to pick out the fact that there's a specific pole here more directly. But that hasn't worked so well. Yeah.
I'm sorry, Kepster, traditional Kepster? Because everything is rotated by 90 degrees. Or do you mean these 90, some Kepster and some 90-degree rotating?
Yeah, 90-degree rotated Kepster. So that here, the actual, so this is work that Marius is actually doing at IBM right now. And what the IBM regulator does is it takes a block of, I think, 9 frames of Kepster, so it's 9 by 13 coefficients, and does LDA on those to get rid of the correlation before it takes features to use for its basic Gaussian recognizer. So what Marius did was taking the same kind of thing, but now you have maybe 9 frequency bands and 13 Kepster at one time. So DCT of temporal envelopes, of log temporal envelopes, and are getting the same 117 parameters and then doing the same LDA and starting from that. And it's kind of nice because it's the same dimensionality, but it's a very different view of the signal. So, but
so another issue with this approach is that this analysis envelope actually kind of recovers the envelope in the temporal domain.
Yeah.
But in speech perception of human, if you just do this, you simply cut off all the pieces. You can still, have virtually no serious distortion in terms of intelligibility. Whereas if you use this analysis, you actually will track this kind of remove waveform envelope. So how does it reconcile with it? The issue is that the envelope directly has a very high variability. Different people who, for the same time, will have different envelopes. Spectrum, the peaks are more regular if you have understand it from whatever the projection is. Whereas the envelope, I think...
I don't know. I mean, you would know better than I about the relative variation. One thing that may pertain to that, though, actually in both PLP and in this domain, you have the opportunity to do the fit in some power domain. So you take the original envelope, you raise it to some exponent, then you do the fit, and you invert the exponent. And if you compress it by raising it to a power less than 1, then it doesn't go so whole hog to just match the peaks, but it's more sort of matching the average level of the signal. And if you have a negative exponent, you can actually end up modeling the values relevant. Getting the exponent right makes a big difference to the utility of both these kinds of features. And indeed, for this kind of stuff, we found the most useful exponents are small, like 0.1 or something like that. So it is more, it's not just picking up the peaks, but it is kind of compressing and getting more of the overall, the average level of the envelope as well. But I don't have these results on here, but we're getting kind of, modest but significant recognition improvements on large tasks. But that means, maybe 5% relative improvement. So which is, it's not massive yet. But one of the nice things about it is that it gives us a whole another angle. Well, Marius has been working with Hynek, who originally came up with PLP, and Hynek is very excited about this because he's always been uncomfortable with the sort of temporal windowing because it's clearly not related to perception. And so the newest idea is to sort of to combine both the LP modeling in time and in frequency in something that Hynek calls PLP squared. And so it's basically an iterative process that we first model the temporal envelopes, and then we have a set of slices across frequency, and then we can model each of those across frequency using PLP to smooth them out, and then we can sort of sample and iterate. And it seems like you get it seems to converge, and this is very new results, and I don't really know if it really does converge or if we'd expect it to. But that seems like this is some idea of a different kind of representation using sort of poles in both axes. I can't remember. Oh yes. So the point about this is that you can tune this so it gives you pretty much the same as what you had already, right? So you can, given that we're doing PLP smoothing across frequency, you could then just take your regular slices. So you end up with some surface and you have to convert into features. You could take slices at the regular 10 millisecond windows, and you should be able to get something which is exactly the same as the original PLP feature. So you can start off at a point where you know your system works already. But then you've got all these different things you can play with, like the width of the window that you're going to do the LP fitting over, the number of poles you're going to use, different compression factors, different representations for things. So it gives us a nice space to investigate where we can move away from just straight up PLP and introduce more of this temporal smoothing and see if we can get something more useful. This particular, so here, what we're showing here is the red lines are with densely sampled in frequency. The red lines are where the pole locations for the temporal envelopes are. Densely sampled in time, the blue points are where the poles of the across frequency LP matches are. And then maybe we can make something out of where these points cross. I don't know what. So it seems like that may be some kind of summary of what's going on there.
Do these locations tend to be shift invariant as you move the larger window along?
Yeah. But for me, what's interesting is when they're not. So the influence of the length of the temporal window. So if I fit, 20 poles in 250 milliseconds versus 40 poles in 500 milliseconds. What happens is that the overall window I'm fitting in is the wiggle room that the LP modeling has got. So it can say, okay, I've got this, I have to put these poles in this much signal, so I'll look at the detail in here and put them where they lie. Or I've got a wider window, and now I can sort of, I can say, okay, well this is where there's more detail versus this part, so I can concentrate them in here. So when there's something like this, where there's a very sharp temporal structure, this is always going to grab a pole, because it's going to get a lot of bang, a lot of error reduction putting a pole there. But as this shifts out of the temporal window, suddenly that pole will be released and will be able to fit somewhere else. So that to me is the most interesting part about this whole modeling thing, is the way that the LP fit moves the poles around based on the temporal window.
Fixed overall window for each frequency band?
Well, so that's something we're experimenting with. And we've done a lot of empirical experiments in terms of seeing what works best with speech recognition. And the sort of 200 millisecond window seems to work pretty well. There was a paper at ICSRP looking at some of those effects by Marriott. There's still, but I don't think we've gotten to the bottom of this yet. But one of the things is we've done it on small vocabulary tasks, and the work we're doing at IBM is looking at the larger vocabulary ears type task. And the results are definitely different when you go into larger vocabulary tasks. So we need to do some more thorough experimentation looking at different, we've got a kind of nice intermediate task that's based on conversational telephone speech, but small enough that we can do a bunch of experiments. So we're investigating that in the future.
So this has been applied to speech recognition scenario for the summer?
Yeah.
So do you have a result or report in that?
Yeah, well...
Oh, yeah.
Like I say, we're getting so he did it on 2 tasks. I don't know if they haven't got the final results that they're comfortable with, but they tried it on conversational telephone speech and also on a noisier task, something else, and comparing it to a PLP baseline, an MCC baseline. In one case it was like 5% better, in one case it was 5% worse. But in both cases, by combining, you get an improvement.
So the feature is still frame by frame.
And I think there was one feature which was this, actually just doing it frequency band by frequency band. But then I think the feature that worked best was the thing that looked most like the LP. So it's still it's very little different. But again, it's just on starting.
So if you were to try to do something that takes advantage of the locations of
Yeah.
How would you distinguish areas where the pole locations almost don't matter because it's basically constant from areas where they do matter?
You mean?
Like on the right there, all the red ones, there's a lot of jitter in there that's probably not relevant to anything.
I don't know. I don't know what we're going to do, but I mean, what I'm trying to think of is a way. So the point is that either of these representations is these are discrete points. So all the blue points is a lot of points, all the red points is a lot of points. But the points where they cross is relatively few points. And there's a sense that somehow there should be some kind of four-dimensional pole-based complex space where we can represent all of that and get the whole thing in just those points. And so that these poles where they don't particularly matter where they'd be broader, softer poles, right? So they wouldn't matter that much, but it'd still you'd have some sort of blob in here that was representing that. I don't know if that makes sense or not, but it seems like there should be some way of using that somehow.
Are you thinking of like an entire window like this being the feature, and then you have like all the locations in that window, or are you trying to think of a completely non-covering feature or not uniformly covering feature that holds it on?
The way we've done it typically is we do a fit over this, and then we take the actual data that falls into the middle, and then repeat it. But that's kind of horribly inefficient. So it would be nice to think of a better way of doing it. But again, you have this. The scope of the window is an important part of the whole process. Okay, let me just talk briefly about these remaining two topics. This one's actually not tremendous. This is not my favorite work. But we've been working on the meeting terms. We've been using the ICSI data. And I was interested, when we made these recordings, we have these tabletop mics, and I'm interested in seeing what information you can get from this, because it seems like something you could imagine being collected quite a lot in real situations, that if a bunch of people come in with their own recorders and they make a set of recordings from different points in the room, you have these sort of low quality but spatially independent samples, but you probably don't know, but you can't rely on good coordination between them. So we did this work of just looking what between channel cues there were. Between channel cues are nice because if you take the differences between channels, you factor out the source spectra, so you get something which is orthogonal to any information you can get from the source characteristics. And we looked at the timing differences and also energy differences. Energy differences turned out to be not very useful because I was doing it on, again, these sort of fairly coarse spectral bins, like bark bins, 15 spectral bins, and there the interaction between the fine structure of the speech and the fine structure of the reverberant transfer characteristics mean that there's a lot of variation in those gains. But the timing differences, or between the phase differences between different channels, worked out pretty well. We did this one thing. Very often when people are doing cross-correlations, if you do a cross-correlation between two signals, there's a strong effect of the overall spectrum of the signal. The actual cross-correlation will obviously be inverse Fourier transform of the product of the Fourier transform magnitudes. So if you have some signal which has got low resonances, then you get a sort of broad peak. So very often what people do is this PAT thing where you sort of basically set all the magnitudes to 1, just keep the phases, then do the inverse DFT. We tried something like that, but a little different, where we flattened the spectrum by fitting an inverse filter. And the idea here is that might actually do better than just setting the magnitudes to a constant value, because most of there's a lot of resonance in the signal that comes from actual resonances in the room. And if we fit that with an LPC model, we're actually, we're exactly inverting those resonances, so we're actually removing the phase effect of those resonances as well. And so you get a very nice, clean cross-correlation signal with very clearly defined peaks coming out here. But we then try to basically we end up with a picture like this. So this is for every time frame, the time differences on the two axes, and we get a scatter plot. These sort of blobs here are the actual speaker, so the excitation is coming from a consistent position. But we also get a lot of noise just in frames where there wasn't a well-defined cross-correlation peak, and you just get some kind of value. So what we do is we then try and filter these points to just get the ones that we're most confident of. And what we did was we looked at the actual correlation coefficient, normalized correlation coefficient, and then took only kept points where the correlation coefficient was within the top half, was above the median in both cases, which cuts us down to about 35 points. And now then we've got rid of most of the outliers.
Can you explain something?
Yeah.
So there's some points that seem like they're the intersection of...
Yeah.
So is that like noise on a particular microphone, like it got bumped or something? Or like why would it be...
These points?
Yeah. So they're the intersection, there where one microphone was completely off, and the other, or misidentified the source. Or it's the person was louder in that microphone, and the other person was louder in the other.
I think, so one of the characteristics of meeting data is there's a large amount of overlap. And I haven't been able to confirm this, but that's what I think is going on. That for this mic pair, this person is closer. And for this mic pair, this person is closer. So when they both speak at once, there's a chance that the cross-correlation in this pair will find something corresponding to this speaker, and the correlation in this pair will find something corresponding to this speaker. So these are the two most common speakers, I think. So that's kind of what you'd expect to see. So that's kind of nice, in that they are generally at those sort of... Each axis is consistent, but they're just different from each other. Over here, these really are just noise and bad stuff going on. But the fact that these are points where the individual correlation is looking pretty good in both channels. It's just that they may not be based on the same signal. Given that there's sort of up to 5% of the time is overlap speak, you'd expect to see something like that. So then we basically want to identify these individual clusters as separate speakers. And so we did spectral clustering, which is just taking an affinity matrix, which is basically finding the points that are close to one another based on something, in this case a Gaussian distance with some radius, and then taking the eigenvectors, the eigenanalysis of this, and in the eigenanalysis of this, the SVD, is going to find the outer product matrices which you can add up to make this. It's going to find these chunks that you can add up and build this whole thing out of. And so it does, when it works well, it does very nicely identifying all the frames that co-occur together. Of course, the further you go down, it will generate as many as you want, but you have to have some way of deciding when to stop, that is, choosing a number of clusters. What we did was we sort of had a way of trying, it was pretty ugly. In the original paper, there's a nice approach, but it didn't work any better than this. So we just sort of tried to look for eigenvectors that look like they're sort of unipolar, so they're either 0 or some non-zero value. And then we look at how many points are sort of above threshold. And that's, if it's working, if it's picking out individual points, then that's sort of the number of points that are involved. And so we just set a threshold on that. So that if there are fewer than 5% of the frames involved, we just stop. And then we get these different classes here. So this gives us classes for the good points, the ones that we filtered out. We can then go back to all the points and assign them to these classes. So even the ones that weren't in the top half of the cross-correlation will still get a label. And we can either do that by just doing it, find the closest class, or we can take advantage of the fact that sometimes one dimension is good and the other dimension is bad, and just sort of look across all the different dimensions and assign the class based on the dimension with that's closest to one of the known dimensions. Here we're only working with 2 dimensions, largely because it was easiest to visualize that way. But of course with more mics you can have higher dimensions here. So we could actually have, however many pairs you've got, you can handle out of the mics you've got. And so we can afford to classify on subsets of dimensions and still get some voting, some consistency. We haven't done it with more than 2, so we haven't been able to get voting to give us a meaningful gain. So this all seems quite nice, but the actual results weren't that good. So there was this missed evaluation where they gave us, I think, 8 different segments of meetings to try it on. And the kind of error we were getting was like 50% frame error of the speaker assignment, which is much better than guessing, because guessing would give you a very low percentage. But it was not really competitive with what the other people were doing, which was, most people were just taking their broadcast news speaker segmentation systems, which looked at speaker characteristics, and just applying it to individual channels. And that was getting down to like 20-30% error. So by using only the between channel characteristics, we can't compete with that, although of course it's completely orthogonal to that, so we can think about combining them and maybe getting a gain like that. Okay. Let me talk about this last topic, which is this idea of collecting personal diaries, or collecting personal recordings. This is actually inspired by the DARPA LifeLog proposal, which I think was itself inspired by Brian Clarkson's work, at the MIT Media Lab. But it's becoming very easy to actually carry around media that records everything, particularly audio, because you can get something. This is what I was using last year, which was basically an iPod that's got a hard disk in there with a microphone, and this is the same thing but just using flash memory. And you don't notice that you're carrying this, and yet it can record 18 hours of audio on 2 AA's, no problem. So you can feasibly, and if you do that, it's still, even if you record 10 hours a day, every day, you're still only up to 100 gigabytes of compressed audio per year of your life.
So what for do you use that? Like students going to a lecture, they record all of
this. I don't think. I think this is basically for recording songs. It's just that what are they going to set as the upper limit? Well, probably no one wants to record more than 10 minutes. But there's no reason to set it at 10 minutes because it turns out you've got enough memory to keep it going. So it's just. I mean, from my point of view, it's just good luck that these devices, they happen to be able to deal with long files, so that they will record for as long as their memory will hold, which is a lot. The deeper question is, and why would anyone want to do this? Which is something I'm still struggling with. I just have this sense that there's something useful that can be done here, but and that we won't. I mean, I was just talking soon about this, but it may be that my hope still is that by starting to work with this data and collecting it, that maybe suddenly that'll become apparent. We now have worked with it for a bit. So I have my student Ken Sub, who carried this thing around for a week and recorded like 60 hours of data, and he's been doing more, but he actually labeled all this data. And the idea was that maybe if we have this data, some use will become apparent. There's things that you can't even think about until you actually have the data available. We're still waiting for that application to strike us. But, something, I still believe it's something that's going to happen, something useful will come out of it. What we have done with this data so far is just been looking at the kind of the coarse, large-scale segmentation kinds of problems. And so, in this case, rather than using a 25 millisecond time window that we normally use for speech analysis, we've been looking at like 1 minute time windows. So now this, 6 hours of data or something is represented as just a few hundred time frames. And then the question is, so what are the kinds of features you'd want to use for that, for windows of that length to be useful? And so we looked at the average energy and the energy deviation, the variance of the energy in each of these sort of ordered 3 spectral bands. And then we have this thing which we call spectral entropy, but it's also related to spectral fatness. Basically, when we say spectral entropy, we look at the sort of narrowband FFT bins that we are averaging together to get the Mel frequency band energy here. And we treat them as a PDF, and then calculate the entropy, so you get a measure of how peaky that measure is, or that energy is. And that seemed like a useful thing perceptually, because the difference between 1 bark's worth of white noise versus a sine tone in the middle of a 1 bark band is a very strong perceptual difference. That was what we were trying to get with that. So that's spectral entropy, and then we can also look at the variance of that. So now we have features, and we can do segmentation. So we tried using big segmentation, which is basically a statistical model to see if you have a segment, where's the best place to divide it up to get, two self-consistent segments, and it also, gives you an index of whether you should divide it or not. And then we have the hand-marked boundaries where Kenseth went in and listened to the whole thing and put down a boundary wherever he felt there was a sort of a significant change, like going from one place to another. And then we looked at the utility of the different features in detecting these things by holding the false accept rate at 2%. So that is approximately, in this case, it's approximately equal error rate, I think. It depends on the relative, total number of frames, total number of true boundaries, relative total number of frames. But so we can do quite well, and we can also, because we've got this kind of task, we can figure out the different combinations of features that do best. In fact, we've gone beyond this now. This is the mean in the DV domain, and the sort of the variance of the spectral entropy measure normalized by the mean of the spectral entropy measure. Those are both 19-dimensional. If we do PCA and reduce them both down to 4-dimensional, then we can get up to 87% here. So there are some things we can improve. So that's looking quite good. And if you look at the results, which I guess I don't have a picture of just yet, but it looks like it does the right thing of finding the right boundaries. The next thing we can then do is try and cluster the segments, again, very similar to the work that Brian Clarkson did. And so now we have, the original segmentation gave us 186 segments, something like this. We can just do the same spectral clustering thing, build an affinity matrix of which ones are similar to each other. In this case, we're using KL distance within each segment. So we then look at the distribution within each segment and see how similar they are by looking at the KL distance, and do some clustering based on that. When we use a 16-way ground truth label, which is actually a little bit condensed from the original labels we had, we can get up to about 70% correct assignment of the ground truth labels at the frame level, which is pretty good, actually. We're quite encouraged by that. So then you could imagine doing this thing where you have this recording, the computer goes away, segments it up, clusters it up, and then it says, well, I found these 16 clusters. What's this one? You give it a label. You suppose you want an example. You give it a label, and then it can go away and label everything else that you've got according to that label. So it could be quite convenient. So the stuff we've been trying to do with this is thinking about how to visualize and how to build a diary type thing from that. So this is this little prototype browser we have, where we've got a timeline here. This is where we have the recording, and this is a visualization where the intensity is based on the average energy, the hue is based on the entropy, and the saturation is based on the variance, or something like that. So we're sort of, trying to boil all the useful features into one visualization. And then we're also pulling information from other, and this is the results of the clustering and labeling. So these points show where the boundaries are found, and you can see again, sort of saying that these boundaries do line up with the obvious shifts in the pattern here, quite convincingly. And then the labels are from the clustering. And so even though there are 3 different segments here, they're all labeled as meeting, which is okay. It's saying that there are changes here, but they all belong to the same class, which is valid. And then we're also pulling in some other information here. So this is from my outbox log, just whenever I send a piece of email, and the first part of the email just sent to. And this is from my calendar. That's what I had scheduled. So I had a meeting with Harry at 2 o'clock and a meeting with Kenseth at 3. And adding this information actually seems quite valuable, and it makes me wonder if maybe this part is more interesting than this part. But the whole, that's, again, it's like really exploring what you can do with this to make it useful. And so you can go back and you can click here and you can listen to the audio and see what happened. Oh, right. So, and one of the things that comes out in this work, just let me mention this finally, is this, this involves carrying around a recorder that's recording everything, and this is not, in many places, this is not considered polite behavior. So I think this is a very serious issue. I mean, because I carried it around for a while, and when I would tell people about it, at least half the people I told were clearly very uncomfortable about the whole thing. And this is actually what killed the DARPA project, right? DARPA were going to do this, and then it got into the press, and people just felt very threatened by it. And so the whole thing was axed, although it's recently reappeared, but in a different form. So I think it's worth, at this point, if people are interested in doing this work, to really try and confront this head on. And so one of the things, again, I've sort of seen it just now, is this idea of, well, maybe it would be more acceptable if you have something that records but doesn't actually keep a reviewable record of what was actually said. And so you could have something which preserves the information you need to do this kind of classification, but scrambles it maybe just by some kind of, standard, well, by some kind of scrambling algorithm, so that you can't understand any of this speech anymore. And then you could make the recordings, and people would find it less threatening probably. And then you could have a more sophisticated version where it only scrambles people who it doesn't recognize, but if it recognizes the voice and knows that it's someone who doesn't mind, then it keeps the actual speech and does the recognition and stuff like that. So that's something we're going to be looking at next. All right, so that's it. Just to recap, LabRosa is about signal processing for audio and machine learning and information extraction for all different kinds of audio. It talked about some different applications in music, basic sort of speech features and other kinds of audio signal features, the stuff we're doing in meeting recording, some of the stuff we're doing, and this project in personal audio. We also do work in music similarity, which I spoke about last year, signal separation, which Manuel, who's been working here with Novosha, has been working on, and various other projects of that kind. All right, thank you. And I'm happy to answer any other questions.